from normal stress, normal strain curve, we have many properties, many concepts that we need to remember. And now I'm going to write out what are the concepts we need to remember here. Points to remember. The first one, as you can see, the proportional limits. So the sigma PL stand for proportional limit. So basically the limit of the normal stress that the material behave linearly. So, and in that case, it's basically a normal stress maximum normal stress that Hooke's law valid proportional limits, because as you remember, the Hooke law is F equal to negative Ks. Okay, so it's linearly portion of the elastic region. And then we have the sigma elastic, sigma E, or sometimes we call it sigma EL, elastic region. So it depends on the book that we have. And that is basically the elastic limits. And within the elastic limit, the material return to the original form if we release all of the stress. So it will be the maximum sigma where material behave elastically, where material behave elastically. And then we have sigma yield, right? Yielding. When the material start yielding, sigma y in there. Sigma yield. And it's either yield stress. And in this case, the sigma where material begins to yield, where begins to yield. And then we also have two more. The first one is ultimate stress, sigma B, I already defined on the graph. And then at the last point in here, when the material break, and that we have it the epsilon rupture, epsilon rupture. So those are the two we need to continue to define in here. The next one is sigma ultimate. Some books say sigma U in there. U is for ultimate, and that is ultimate stress. So basically the maximum stress that the material can carry. So it will be maximum sigma or sigma max. Sigma get the maximum. And then the last one is epsilon rupture. R is the rupture strain. And in that case, it's basically the fraction strain. So the material it break, right? So it will be fracture strain. So those are the points to remember when we talk about the material properties. And when we have those points to remember, we have a few material properties that we briefly mentioned earlier, but now let's put into detail for this one. So some material property that we need to remember. After learn all of that new concept, proportional limits, elastic limit, yield stress, ultimate stress, rupture strain. So the first, we want to, for example, want to know what is the stiffness of the material. To measure the stiffness of the material compared to the other, then how can we find out the stiffness of material? We will compare the Young modulus. Or modulus of elasticity E, right? E capital, Young modulus. So between the two members, if you see the material have a slope more, if another material, I just put it in green here, another material that have the curve above the blue curve, then the material that have in green curve have higher E, it means it's stiffer. So stiffness, that material, we call it stiffer. So measure stiffness of the material using Young modulus. And then to measure the resilience of the material. Resilience of the material. What does that mean? Resilience means that when you apply certain force, certain event, the system or the material can get back to the normal as soon as possible. That is in the real life, basically the basic concept of resilience. For this one, for the material perspective, the resilience is the measure of the area under the elastic portion of the curve. So that the areas we want to measure the resilience under the elastic portion of that curve. Okay, so that the resilience, because at that portion, when you reduce the stress, the material will get back to normal. So that we call resilient. And just like COVID-19, the country that more resilient is mean quicker to get back to normal. So to measure that, it will be the area under the elastic portion of the curve, right? So the areas under the elastic portion curve. And then measure how tough it is. Then measure the toughness. To measure the toughness, we measure the area under the entire curve. Area under entire curve. Area under entire curve. So that the areas for the whole thing go proportional limit go up here. See that? And the entire curve in there. So the area between the blue line, blue curve, and the green horizontal, that is the areas measure the toughness of the material. To measure the strength of the material. So basically, we measure the ultimate stress. So which material is stronger. It depends on their ultimate stress. So that it will be sigma ultimate, not sigma yield, sigma ultimate. And two more. Find out the two type of material. Material is very brittle, and some material is very ductile. So steel, for example, is very ductile. Aluminum, so that to measure the ductility of the material, it will be if they have the large rupture strain. For that material, it need to be the large rupture strain. What is the rupture strain? It measures basically epsilon rupture as defined earlier in there, the rupture strain in there. So the two material, the rupture strain is bigger, we say that material is more ductile. And the opposite of the ductile, it will be the brittleness. So for brittleness is the opposite. So as you can see, it will be small rupture strain, small. What material in civil engineering that have a small rupture strain, just like concrete, very brittle. So those are the material properties that you need to know. 6 measure of the material properties: stiffness, resilience, toughness, strength, ductility, and brittleness. And that with different associated measure that you already know in there. So when you compare, for example, the toughness, you need to compare the area under the entire curve for the 2 or more material to see which one is tougher. So with that, we are about to finish this just with one last thing. Sometime, as you can see, basically to in the lesson number 2 to find out the failure level, it refers to the sigma yield if it normal stress, right? Sigma yield. How to define sigma yield? So as you can see, the PL proportional limit, sigma PL, sigma E, sigma Y are very close together. So it's very difficult to differentiate between those. So how to determine the sigma yield so that in the failure level when you design for the structure. So with that, we have a method that you can use to define that, and that method call it point 0.2% offset method for finding sigma yield. And that is method because that is the failure level normally we design. Just go back to the design and analysis we did in the previous lesson basically. So when we applied, and you can see when the normal stress, normal strain curve, normal stress and normal strain curve does not exhibit a horizontal portion. What I mean horizontal portion here. Then how can we find out the yield stress? So you can see for the typical material behavior in the yielding, the curve here is in horizontal, right? And that easy to they start horizontal curve that we can find the sigma yield, but some material don't behave that way. The yielding is difficult to see the horizontal curve on that portion. It's difficult to recognize in the graph of sigma and epsilon. So how can we find that? That method we call it 0.2% offset method for finding sigma yield. So let me put you one scenario for the sigma and normal stress, normal strain curve. So it's epsilon and sigma and epsilon, normal stress and normal strain curve. And that the curve, the yielding is difficult to see. So let me, the horizontal line portion they're not exhibit. For example, this is the behavior of that material, and then they rupture here. The question is how I can determine the yield of this. So it's based on the 2% offset limits. It means that the epsilon, get the epsilon at 2%, 0.2%, it means 0.002, and that basically 0.2% of the strain, and you will draw a line parallel to the proportional line of that curve, parallel to the proportional, okay, the linear portion. Go to, and whatever it hit the normal stress, normal strain curve of that material, you can get back to the vertical here, and that basically you find out the sigma yield. And by the way, this one, if you recall, that is the sigma ultimate. So that the sigma yield here is basically the way we find out if we use 0.2% offset method to find in sigma yields. When the horizontal portion of the normal stress and normal strain curve does not exhibit, then we use 0.2% method. If it exhibits like this, so you can see, okay, where is start of the horizontal line, horizontal curve, then you can go ahead to pick that number to find out the sigma yield, the yielding stress. With that, we finish this lesson and go to, we have two problems today, worksheet 3A and 3B, and also you go ahead to review the lab and prepare with the team to do the lab, tension lab.